Hello, everybody. I'm Chris Carberry, CEO of Explore Mars. Welcome to our third H2M seminar, Perseverance Preparing for Launch. Before I introduce today's moderator, I have a few short announcements. First of all, if you haven't checked them out yet, Explore Mars is co-hosting Janet's Planet Online Astronaut Academy, weekdays at 10 a.m. Janet's put together an extraordinary student programming. So if you haven't checked it out yet, even if you don't have kids, I think you really should. It's really quite spectacular every day, so certainly worth tuning in. Just a reminder, the Humans to Mars Summit is now taking place on August 31st through September 1st at the National Academy of Sciences building in Washington, D.C. Registration and other details will be open again soon. And I should also note that every webinar we're doing, we're acknowledging our H2M sponsors. Not all of them each time, but we're doing, trying to acknowledge all of them over the course of these webinars. Today, I'd like to acknowledge Aerojet Rocketdyne, Lockheed Martin, Northrop Grumman, ULA, Paragon, MDA, National Institute of Aerospace, and the Science and Entertainment Exchange. So thank you very much for everybody who's sponsoring the Humans to Mars Summit. Lastly, if you have any interest in sponsoring this webinar series, or even an individual webinar, please reach out to us if you have an interest. We'll post some information on this shortly, but anything people can do would be greatly appreciated to be able so we can actually continue to do these as well. Since we're not charging admission for these webinars, any sponsorships or donations people can do would be greatly appreciated. So without further ado, I'd like to introduce you to our moderator of today's session, a longtime friend of Explore Mars, Mary Angola, the manager for space communications at Aerojet Rocketdyne. Mary, thanks for leading our panel today.
My pleasure. Thank you so much for joining us today. We have a wonderful lineup for you, and I'm very excited to welcome all of our guests. So during my day job, I get to tell stories. And so today our panel is going to tell the story of the Mars 2020 mission, and specifically the Perseverance Rover. Recently, the rover was named after a Name the Rover contest that NASA had with over 28,000 entries. And so quite an enormous amount of support for this. And I think the name Perseverance is really fitting for this rover because it's going to face a lot of challenges on Mars, but it's ultimately going to make discoveries that will pave the way for human exploration to Mars. During my day job, I work a lot with NASA's Space Launch System, and that's the big exploration rocket that's going to take us to Mars one day. So the Mars 2020 rover is slated to launch this summer from Florida on ULA's Atlas V rocket. It's going to launch in a 541 configuration, which means the 5 represents the diameter of the fairing. So it's going to be a 5-meter diameter. The 4 is how many strap-ons. And so in this case, it has 4 solid rocket motors built by Aerojet Rocketdyne. And the 1 is the single engine Centaur. And so that'll use the RL-10 engine. And I want to give a shout out to the RL-10 team in West Palm Beach. They recently celebrated their 500th flight of an RL-10 last month on another Atlas V launch for the DoD's Space Force mission. So the Perseverance rover's got a really reliable upper stage engine that's going to take it to Mars. And so very excited for that. So without further ado, I want to introduce our panelists. Our first is George Tehu, and George is the program executive for Mars and lunar exploration at NASA headquarters. And second, we have Katie Stack-Morgan, who is the Deputy Project Scientist of the Mars 2020 rover or Perseverance at NASA JPL. And last, we have Neil Tice, who is the Mars 2020 Perseverance Aeroshell Program Manager at Lockheed Martin. So without further ado, welcome, George. And can you tell us a little bit about yourself and your role in the program?
Certainly, and thanks for having us all here. Looking forward to talking about the mission. So I've, in my role as a program executive for this mission at NASA headquarters, largely what I'm doing is helping to keep the mission going, making sure that all the activities are moving down the field. The real hands-on work is done by the project team, which is a jet propulsion laboratory and and a variety of other places with our partners, like at Lockheed Martin, where Neil is, and a variety of other places. And I've been at headquarters for about 20 years. Came in after spending some time doing some commercial space, a bit of military space, international cooperation, and then became a Martian in 2000, and have been loving it ever since. Got an opportunity to become a lunatic for a little bit and be do some lunar missions on working some instruments and on the Lunar Reconnaissance Orbiter, and then came back to Mars. And so I've been working on this particular mission for a little over 8 years.
Thank you, George. And we love our Martians. So next I want to introduce Katie, who is at NASA JPL. I'm going to give a shout out to JPL. If you've never been to their website or downloaded any of their apps, I highly encourage you to do that. They have wonderful public outreach tools. So Katie, do you mind telling us a little bit about yourself and telling us what your role is?
Sure, thanks, Mary. Well, thank you to Explore Mars for having me today as a speaker. As Mary mentioned, I'm the Deputy Project Scientist for the Mars 2020 Perseverance Rover. And that means I'm one of the scientists, part of a science leadership team at JPL, helping to develop and operate the Perseverance Rover. And so our rover missions are usually made up of engineers and scientists. And so I'm on the science side. And so I help lead a team of over 350 scientists as we figure out what we're going to do on Mars, what science we're wanting to accomplish, and also helping the engineers design a spacecraft that can meet our science objectives. And I'm very excited for Perseverance and what it's going to accomplish on Mars, and also as the first leg of a potential Mars sample return campaign to bring samples from Mars back to Earth. And I came to Perseverance from after working on the Curiosity rover. I worked on the Curiosity rover as a graduate student at Caltech, and then moved up the freeway to JPL to continue working on that mission, and eventually got pulled over to Mars 2020 and Perseverance. And so I'm very excited to bring my experience and working on Curiosity to Perseverance as we continue to explore the surface of Mars. And so we have great things ahead of us with this mission, and I'm excited to share that all with you today.
Thank you so much, Katie. I can't wait to hear more about the science. I'm very excited for that. So our third panelist is Neil. Neil, welcome, and we're glad to have you. You want to tell us a little bit about yourself and your role on this mission? Neil, you might be muted.
All right. Thank you for the introduction. As Mary mentioned, I'm the program manager for Mars 2020 Aeroshell. I was also very heavily involved with the Mars helicopter delivery system that we'll get into a little bit later. I've been at Lockheed Martin now for almost 36 years. I actually started with Martin Marietta quite a few years before. Actually, about 3 years out of college, I had worked for Caterpillar Tractor Company for 3 years as a mechanical engineer. Caterpillar was a very good company, but I always wanted to move beyond mechanical and get into aerospace. When I graduated, I wasn't able to work for Martin Marietta at the time because they weren't hiring, but in 1984, they did manage to hire a lot of engineers, and that's when I started working for them. I've been working NASA programs for pretty much a majority of my life now at this point. Some of the first NASA missions I worked on were Magellan, TOS, MGS, GRS that flew on the Mars Observer, Chandra. I was the mechanical lead for the ACES instrument. It's the primary instrument on Chandra. Worked on Mars Pathfinder IMP camera, Odyssey, Genesis, MRO, Phoenix, Maven, InSight, many NASA missions, and 9 missions to Mars. So I'm probably one of the most experienced Mars people on the program. Currently, I'm the program manager for the Dragonfly New Frontiers mission. We just recently started that one. We're currently in phase B and getting ready for our system requirements review. So I tend to get involved very early in these programs and stay pretty much through the end of the missions. In fact, there's still missions that are flying right now that I worked on at one time, including Chandra, MRO, Maven, and Insight.
Wow, that's awesome. Thank you.
You're welcome.
All right, so let's get into the meat of this panel. So I want to first talk to George a little bit about the technology on the Mars rover. You all always at NASA put such great technology. I remember Curiosity had a laser on it, and everybody was really excited about the Curiosity laser. And so I want to know more about the Perseverance rover and the interesting technology you put on board at this time.
Yeah, there is so much going on with this mission. We have a lot packed into it. And as you noted, we're headed towards the launch pad here in July. But the story of this mission and the choices we had to make on what types of technology or what types of science instruments, that story starts a good 8 years ago, shortly after the Planetary Decadal Survey came out and said that one of the top priorities was to, for the coming decade of planetary exploration, was to do a rover that would be capable of starting a Mars sample return, to be able to go to a landing site on Mars, select rocks that could potentially preserve any what we call biosignatures, records of an ancient environment that might have given a clue to life potentially being on the planet, and starting that process of bringing it back to Earth. But even further back, there was, you have to go even further back to where this capability comes from. We often talk about standing on the shoulders of giants in all our advances, and this mission is a good example of that, in that all the prior missions we've done, the robotic missions, have all been building not just in terms of the scientific knowledge that we've been gaining, but also the technology and the capabilities. And so it's really now is the right time for us to be able to do this type of mission through both what we learned from the prior missions, understanding, and actually if you could pull up, we had one image on chart number 1. This illustrates it a little bit of what all of our missions have been going towards. In our robotic program, we have 4 key goals. We want to, first among equals is trying to answer that age-old question, could life ever arisen somewhere else beyond Earth? And we're looking for that at Mars. Then just understanding the planet itself, understanding its climate and its geology. And for a long time, we've always been trying to do what we can with these robotic missions to prepare for future human exploration. And so as we progressed through that, there have been these evolving themes. The first along that line was the hunt for water. Had there been a watery past on Mars? And those early missions, particularly the Mars exploration rovers, determined, yes, indeed, Mars had a watery past in its ancient time. And then we were able to move to, well, all right, was those early environments even potentially habitable? And the Mars Science Lab, Curiosity, helped answer that question. Yes, indeed, it was able to find in the record of the rocks, a record of a habitable environment. So now we're ready to take that next step, seeking the signs of life directly onto the surface. So if you can go to the next chart, that goes to what are we doing and what types of equipment are we trying to put on this particular mission. We have 4 key objectives. First is to understand the geology of that landing site that we're planning to go to, conduct in situ astrobiology and look for those potential signs of life, put them in a cache that we can potentially go back with a future mission. And again, we're going to be continuing the experience and practice of taking measurements to prepare for human explorations, but now we're taking it the next step, something we've never done. We're actually testing technology that could potentially be useful for future human exploration on Mars. So all of that goes into deciding what type of science instruments. And I want to leave let Katie go into some of the details on the science instruments we picked, but they're all geared towards finding those potential biosignatures. But I will jump in here about the interesting technology demonstration we're doing to prepare for future humans, and that is an experiment that's actually going to generate oxygen on the surface of Mars. If we're ever going to send humans, we'd really rather be able to live off the land as much as we can and use as much resources at Mars as we can. And fortunately for us, Mars has an atmosphere. While it doesn't have much oxygen, it does have a lot of carbon dioxide. So if you can split that apart, you can extract some oxygen. And that's exactly what we're doing with one of our experiments called MOXIE, which is going to suck in that Martian atmosphere and split apart the carbon dioxide, and we're going to be able to actually measure the purity and the amount of oxygen that we can get out of it.
That's great, George. So I do want to come back to you later, though, to hear a little bit more about the helicopter that you're going to have. But since you've you started to talk about science, I want to give Katie a chance to jump in and talk a little bit about the science that we expect to receive from Perseverance, and how some of the science is different than the science we did have earlier with Curiosity and Spirit and Opportunity. So I'm gonna let Katie jump in if you don't mind.
Yeah, so Mars is a fascinating planet and a fascinating planetary experiment. We know, based on what we know about Mars already, we think that it once had a surface environment that might not have been that different from our own planet here on Earth. At the same time, Mars also had incredible processes like impact processes and giant volcanoes. And we want to learn more about that geology with the Perseverance rover, understanding some of the major, surface processes that Mars experienced. Impacts, volcanics, history of water on the surface, and we can do that with Perseverance. But of course, the real key and kind of key of this mission is the search for ancient life. And George mentioned biosignatures, which are basically any kind of pattern or texture preserved in the rocks that indicates that life might have once been there. And with the Perseverance rover, we have a very unique payload, different from previous missions, that makes us uniquely well suited to searching for signs of biosignatures in a way that previous rovers have not been able to. So if you pull up slide 5, which is an image of the rover and its payload, I just wanted to point to some of the features and instrument payloads that make this rover so unique. So if we can get slide 5 up. What I want to highlight as we're waiting for that are the instruments on the arm of the rover. So the rover has instruments. It has instruments in the body of the rover, as well as the mast, which is the head of the rover. But what really distinguishes this rover from previous rovers are the instruments that we carry on the rover's arm, which are out there on the end there, nearly touching a rock. And the instruments I want to mention are the Pixel instrument, which is an X-ray spectrometer to look at the chemical composition of the rocks and soils, as well as the Sherlock instrument, which can look at organics and the composition and mineralogy of the rocks. And what's different about Perseverance compared to rovers like Curiosity is that Perseverance can actually map very fine scale textures with very fine scale composition and organics. And that kind of mapping in combination of textures and composition is exactly the way that we search for biosignatures in ancient rocks here on Earth. And for the very first time, we can do that on Mars in a non-destructive way. Previous rover missions have ground into the surface, collected powders, and looked for things like organics. But in doing so, they've destroyed some of those fine scale textures that are essential for making the case for a biosignature. And so with Perseverance, we have an instrument payload that it uniquely suits us to looking for signs of ancient life on Mars and making the best decisions about the samples that we're going to collect and hopefully bring back to Earth to really answer that question: did life once exist on the surface of Mars? And so we're really excited about that. And so of course, the search for life is a main objective for us, but we also hope to learn more about the evolution of Mars as a planet and the processes that turned Mars from a planet that may once have been habitable into the kind of cold, barren desert it is today, and understand the story of a planet as it evolves. And we can do that in situ on the surface with Perseverance, and also with those samples that we hope to bring back.
Oh, that's amazing, Katie. I can't wait for this rover to make it there. So George, I'm going to go back to you because I want to hear about the helicopter. I'm excited about the helicopter as a technology demonstration. So can you tell us about what it's going to do and what its purpose is?
Yeah, absolutely. Interesting history. When we put out the call for what types of science instruments we want to have on this, it was very broad and technology investigations. There was actually an idea to do some sort of helicopter that was proposed. Turns out wasn't quite ready yet, but it was worthwhile doing some technology investment in it. And so a few years went along, and JPL, who had proposed it, actually did make quite a few advances, and they got to the point where, yes, it was definitely viable. So we made the choice that this is a good example of a very high risk but high reward opportunity to have a secondary payload. You don't get a chance to go to Mars very often. And while the rover itself and our objectives for seeking signs of life and doing our other objectives are the prime mission, it created an opportunity that the helicopter could ride along and do its own demonstration of, is it possible to actually start having a new dimension of mobility at Mars, now in the aerial dimension. So fundamentally, it's going to, the size of it is, I can hold my hands up, the body of it is a little bit, almost CubeSat size, one cube a little bit bigger, but it's solar powered, has 2 counter-rotating rotors that about a little over a meter in diameter. And what we do is we carry this on the bottom of the rover. After we've landed, we'll be able to deploy it, and it'll, in the first earlier parts of the mission, that's really our opportunity to do a few test flights. So it's a fairly short duration demonstration opportunity. Couple of test flights, taking it slow first, small hops, then trying to go push some of the capabilities beyond that. And really looking forward to seeing how it operates actually in the Martian environment. We've been able to effectively fly it in simulated environments here on Earth in vacuum chambers, but now seeing how it really works on the surface of Mars, trying to communicate to it. We have to communicate through the rover. It's our relay to speak to the helicopter, and it'll do a couple of demonstration flights and potentially pave the way for future missions that might use a similar technology.
Wow, that's great. I'm very excited about this. So George, your team helped work on the deployment mechanism for the helicopter. So can you talk a little bit about what that is and what that entails? Not George, I'm sorry, Neil.
Sure. If you could go to slide, let's see, 15. So before I get into it, about 2 years ago, JPL came to Lockheed Martin asking if we could work on this Mars helicopter delivery system. They had a concept of putting the helicopter on the belly pan of the rover. And so we took that concept that was basically just a bunch of drawings that somebody had come together to install it onto the belly pan, and matured that design to the point where we could start building hardware. What you can see on the bottom of this picture is you can see the belly pan of the rover, and you can see a large black object, which is the debris shield that protects the MHDS or the helicopter during landing. So I think you'd like to know a little bit more about how this operation will work. Well, the first operation, once the rover is on the surface and spent about 30 days checking out all the various subsystems, they'll be ready to drop the helicopter. So the first procedure in getting that helicopter onto the ground is to drop the debris shield. If you could go to chart 25. Okay, you can see the front view of the rover like you saw previously. You can see the debris shield in the top picture. There's a cable cutter that will be fired to release that belly pan or the debris shield so that it drops down to the surface. The rover is now able to drive away from the debris shield to get it out of the way. And then that starts the process of releasing the helicopter from the belly pan. There's some launch locks that fire initially to kind of release the helicopter. There's another release mechanism that will be fired to allow the egress arm to rotate downward. In the picture C, you can see how now the helicopter is at least vertical. There's another set of mechanisms that have to be fired to release the legs. So you can see the first two legs have popped down and then the second two legs. And then the final release is another frangible bolt, which is fired that allows the helicopter to drop down to the surface. The helicopter has very springy legs that allow it to just kind of bounce, and it just need enough clearance that the rover can drive away and leave the helicopter sitting on the ground.
Oh, that's awesome. I'm looking forward to that, Neil. So I want to move a little bit more to launch now and talk with Katie, if you don't mind. How's the science team preparing for launch? Especially, how are you able to accomplish all the tasks you have to do with so many of you probably working from home right now?
Yeah, fortunately, Mars rover scientists are very used to working from home or from different parts of the world. For curiosity and opportunity and spirit, our science teams are spread all over the world, and we call in every day to work together to operate rovers. So in a lot of ways, we've been preparing for this type of situation for a while. And so, we're continuing to work from our own, dispersed locations. But our science team right now, we're gearing up for launch and getting excited for landing. And what that means for us on the science side is really digging into the data that we have about our landing site and learning as much as we can about the geology of our landing site and doing as much preparation and planning as we can before we get there. Because the minute we land on the surface, we're going to have a lot of decisions to make. Where are we? What rocks do we think we're looking at? Where do we think we're going to drive? What's our first stop going to be? What's our first sample going to be? And so we kick off this whole series of decisions. And so the more prepared we can be to make those decisions, the better off we'll be when we're on the surface, when we're also experiencing the, being on Mars for the first time with this rover and checking out the instruments. And so the more prepared we can be, the better. And so what our science team is working on, we recently finished the construction of a geologic map of our landing site. And so mapping is something that geologists do here on Earth to understand the geologic history of rocks here. And so we did that for our landing site, but using orbital data, so images taken from orbiters around Mars. So we created this geologic map, and now what we're doing is we're digging into that map to identify the very specific locations and questions that we want to ask with the Perseverance rover, and trying to find those spots where we think we can answer those questions, which units we're going to look at, which minerals we're interested in studying, and where do we think the best exposures of those locations are. So we're working right now with the science team to come up with a science mission plan for what we're going to do on the surface, and identifying the questions, the locations, and the potential samples, and even coming up with representative rover traverses to anticipate what we're going to do when we land on the surface. So of course, when we get to Mars, we're exploration driven and discovery driven, and Mars always throws a few curveballs at us. But the more we can do right now to prepare and be ready, I think the better we'll be at operating efficiently on the surface and accomplishing our science objectives. So that's what the science team is working on now. And actually we had a telecon going just before this webinar that I was dialed into, and we were talking about, objectives for atmospheric science. So we meet every couple weeks and we have conversations like that with the science team. So we're going full steam ahead on those preparations, and we're excited for landing and launch.
That's awesome. I had forgotten that you're used to working remotely. So that's really good that this isn't slowing you down.
Yeah.
So George, can you tell us sort of what are the next major milestones before launch?
Sure. Actually, if you can pull up chart number 3, it gives a timeline of kind of where we've been and where we're going in terms of the progress of the mission. We've been designing, building, testing the rover for the past couple of years. And now pretty much all the hardware is down at Kennedy Space Center being prepared for launch. A lot of, we've actually already got the rover is finished its functional checkouts and is had its various deployed components stowed, getting ready to be stacked together with the other components of the mission to prepare and putting it in the configuration that we call the cruise configuration. That's the image you see there where it says cruise to Mars, where we have the rover packed inside the aeroshell, and then what we call the cruise stage attached with the aeroshell that helps get it to Mars. So actually, if you can go to the chart number 6, this shows some of that testing that has been going on. Now, this is not at Kennedy. This is prior to that. This is our first driving test of the rover, and then also putting all the components together and putting it through a space simulator, simulating the cruise to Mars. So as much as we can do to simulate the journey to Mars, we're trying to do on Earth. Can't quite do everything, but we can come as close as you can to it. If you go to the next image, this is where we are today. And this is our rover at Kennedy Space Center getting its weight checked. We call this a mass balance. We put it on a rotating platform and make sure that we fully understand where the center of gravity is, have to put on some ballast mass in certain places. And that's now complete. So you can see the rover is all tucked up. And I will point out here, you can see our nameplate right there, Perseverance, looking mighty nice on the robotic arm. So the team there at Kennedy is preparing the spacecraft to get it in that cruise configuration. Over the next couple months, once we get it all put together, then it will be integrated and encapsulated with the launch fairing that United Launch Alliance provides our launch vehicle, the Atlas V that you described earlier. It'll be put into that launch fairing, and then that whole component will be transported to the Cape Canaveral Air Force Station side of the launch area. We're going to Launch Complex 41, which is where we'll launch out of. Take that whole component to what they call the vertical integration facility, right next to the launch pad. Then that whole, the fairing with the spacecraft inside it will be hoisted up, put on top of the Atlas Centaur rocket, and then we await our launch date for rollout and launch. Our launch period opens on July 17th, and we're getting ready for that. Now, I want to throw in, point something else out. Katie mentioned how her team, at least the science team, is used to working remotely. A lot of our Outload team, of course, is not. And when you're doing the hands-on work, that can't be done. I think a lot of people are asking the question, how is the team handling this new environment where a lot of us are needing to be remote? And roughly a majority of the team is now doing teleworking. There are the small numbers of teams that are needing to, who are the mission critical, finishing up a couple of pieces of sampling hardware at Jet Propulsion Lab, but the majority, a lot of that effort happening there at Kennedy. And I do want to point out across the agency, the first priority has been to the health and safety of our workforce and also the communities that we're around. So we've been very successful so far in making sure that both our team and the communities they're in are operating in a very safe manner.
Thank you, George. I'm glad you all are staying safe. Before we move to landing, because I'm seeing a lot of questions coming in asking about the landing and operations. But Neil, I just wanted to check in with you if you had any fun facts you wanted to share about the launch.
Oh, it looks like somebody already unmuted me, so I don't have to. So yeah, I've got one fun fact that is kind of fun to talk about. The ride on the Atlas 541 is a pretty rough ride, and the payload gets exposed to up to 6.5 Gs of axial acceleration during the launch, and up to 5.5 Gs of acceleration laterally. So it's a pretty rough ride, but believe it or not, that's not the roughest ride it's going to see. The real rough ride occurs during entry, descent, and landing, whereas the aeroshell hits the atmosphere, there's a deceleration of up to 12 Gs, which puts an extreme load on the front of that heat shield as you're slowing down. And that's really the design requirement for the aeroshell, was that 12 G load. So that's kind of a fun fact that normally launch is the worst environment, and in this case, EDL is the worst environment. Another fun fact is during launch, it's very noisy if you're to be right next to that launch vehicle. And a comparison of how loud that noise level is would be if you were standing right next to a jet engine on takeoff. That's how much noise is generated by the rocket engines on the Atlas V. And so it's a pretty noisy atmosphere that creates all kinds of vibrations inside the fairing where the payload is sitting, and can see up to 18 Gs of vibration just from that acoustic level on the launch pad. And then I guess the last fun fact is the Atlas V really has to get going fast in order to escape the pull of gravity from the Earth. And in order to get headed on its way to Mars, it has to achieve at least 25,000 miles per hour of velocity before it gets away from the Earth and on its way to Mars.
Thanks, Neil. I'm glad we had those facts. We're ready come July 17th to share those tidbits with our friends. Yeah. So Katie, let's talk about landing, because I think that's what folks want to know about. And so we'll get into the technology, but let's talk about sort of the science in picking a landing site. So you mentioned earlier there are orbiters around Mars. So we've had 8 successful US landings with landers and rovers, but then we also have these orbiters, and probably one of my favorite is the Mars Reconnaissance Orbiter, which has the HiRISE camera, and it took a gorgeous image of Victoria Crater back in 2016. And I think everybody knows that image. It's kind of an iconic image of Mars, at least in my mind. And that really helped the science team look at the terrain that Opportunity was going to have to traverse. And so you spoke to these orbiters and how they play a role. Can you talk about the landing site for Perseverance? What is it called? That was one of the questions that's come into us, as well as some of your decision making that went into picking that landing site and some of the challenges with it as well.
Yeah, absolutely. And so if we can bring up slide 17, I think I'll start there. But our landing site is Jezero Crater, and you can see that here. And I'll mention that the selection of our landing site was the culmination of a 5-year process involving the community, the Mars community, and any other interested folks in the community who wanted to weigh in and provide perspective on where the right place was to send the Perseverance rover. And so the result of that 5-year process was the selection by NASA headquarters of Jezero Crater as the place to go with Perseverance. And so what this image shows, this is topography of Mars, shows the location of Jezero relative to some of the other big geological features in the area. So Jezero Crater is on the inside rim of one of the largest, oldest impact basins on Mars, and that's the Isidis Impact Basin. And we think that the Isidis Impact Basin formed about 3.9 billion years ago. So these are old rocks here. And this is one of the major impacts that we think happened on Mars. But not too far away from Jezero and Isidis is Syrtis Major, which is one of the major volcanic centers on Mars. And so Jezero Crater has this unique position, being very close to major impact related terrain on Mars, but also close to a major volcanic center. And if we go to the next slide, what is particularly special about Jezero, in addition to this general setting, is the presence of a delta within the crater. And we think that Jezero Crater was once the site of an ancient lake basin. And there are a number of places on Mars that we think might once have hosted ancient lakes. But what's really special about Jezero Crater is that it's a slam dunk. We have not only the delta that we see, and we recognize landforms like the Jezero Delta here on Earth and deltas that we have here, but in this crater, we have an inlet valley, which tells us that water flowed into the crater. But what is unique about Jezero is that it also has an outlet valley, and we don't always see that in craters on Mars. So we know that this crater once filled up basically like a bathtub to the point where it overflowed out the outlet valley. And so that's really important for us as we're thinking about what a good landing site might be, because not only do we have evidence in the rocks in the delta that a lake was there, but we know that there was enough water there for a significant amount of time to basically fill this crater and then overflow it. And sometimes we think in different places on Mars that water might have been a kind of figurative flash in the pan. But here in Jezero, we know that that water was around long enough to fill the basin. And we think that might have been a great place for life to exist and take hold. And we have the types of rocks, similar to rocks here on Earth, that are very good at preserving that evidence of life. And deltas here on Earth are great places to go to look for organics. And we hope that the same is true here in the Jezero Delta. If you advance to the next slide, I'll just point out that the other thing that's really unique about this location, and this, what you're seeing here is a false color image from one of our orbiter spectrometers. So this is an instrument that tells us about mineralogy. And the colors highlight the fact that there's a lot of mineralogical or compositional diversity here in Jezero Crater. And what you see here in green, those rocks there on the inner margin of the crater, those rocks contain carbonate. And when you think about carbonate, you might think of reefs in the Bahamas or in Australia. And honestly, that's kind of what we think about too. We don't know that that's what we have here, but we have carbonate rocks in what was perhaps a shallow lake environment. And that's a great place for both hosting life and preserving life. And so we're really excited about Jezero Crater for a number of reasons. We know it had water for a significant amount of time. It has the rocks that are really good at preserving evidence for life. And we have a number of very interesting and unique geological and astrobiological targets here in this location. And another special thing about deltas is that they're really good at concentrating and collecting rocks from a large area into one place. And so that delta right there represents, and sediment grains in that delta came from very, very far away outside the crater. So by going to this one location in the crater, we can sample locations far, far away that we might otherwise never have been able to go with the rover. So deltas are really good at concentrating a geological story in one place. And so these are some of the reasons why we've been so excited about Jezero Crater and the potential for exploring this with the Perseverance Rover and helping us understand the surface of Mars and Mars's potential for hosting ancient life.
Wow, this is great. So I think a lot of us know landing on Mars is really difficult. And so Neil, I want to ask you about why is it so difficult to land on Mars? And then can you tell us about the aeroshell and the heat shield and how that's used to protect the rover during the landing?
You could go to chart 10 for me. Thank you. Okay, so entry, descent, and landing is a very complex process. There's lots of things that have to go right in order to get down to the surface. And that's one of the things that makes it so difficult. And there's been a lot of failures at Mars. Fortunately, JPL's been very lucky at getting most of their spacecraft to Mars, but some of the other countries that have tried have not been quite so lucky. Just to give you an idea of the complexity, the spacecraft essentially takes 6 to 8 months to get to Mars before it's ready for the entry phase of the mission. And the first thing that you have to do is separate the crew stage from the aeroshell. And so now the aeroshell is floating on its own, heading towards the atmosphere. It does have thrusters to adjust the angle of the spacecraft, of the aeroshell as it hits the atmosphere. Since it was previously installed on the cruise stage, we do have to adjust the center of gravity of the aeroshell before it hits the atmosphere. And We do that by deploying a bunch of very heavy tungsten masses. There are actually 2 tungsten masses that weigh about 164 pounds each. And that sets the gravity where it needs to be as it hits the atmosphere. The spacecraft is really on its own at this point. Everything is robotically controlled and pre-programmed, which means you have to do it right the first time. There's no joysticking this spacecraft as it comes in. So as you hit the atmosphere, the aeroshell is the primary protection for the rover that's inside it. There's a peak heating phase where the heat shield gets to about 3,500 degrees surface temperature on the outer surface. And that aeroshell protects the rover from seeing those high temperatures. There's a thermal protection system called PICA that protects the rover by ablation. It allows the heat to flow away from the spacecraft, and the back shell also does some protection there. But once you get through that peak heating, now you're just kind of coasting. There's some additional balance masses that are released. 65-pound masses are ejected from the aeroshell. And that allows us to kind of surf our way through the atmosphere to the final landing point. And so it's actually, very ingenious. There's lots of things going on during EDL. All of these have to happen just right. The next major event would be to deploy the parachute. Parachutes seen a lot of testing. We're very confident in this parachute. JPL did all the testing, but there's always things that can go wrong with parachutes. And then after you've coasted on the parachute for a little while, then the heat shield is released from the rest of the structure. And there's some very good videos on YouTube showing the MSL heat shield leaving the back shell. And that allows the radar to turn on at the right time to see how far above the ground you are and determine the final landing points. There's lots of cameras on board that are used to optically navigate the spacecraft to a safe landing zone. The Sky Crane was developed by JPL to allow various separation hardware to fire and lower the rover down to the surface so that it can fly away. So all of this has to happen in 7 minutes. So anytime one of these happens, it's just very exciting. There's lots happening and lots that has to go right. So as soon as you hear that, the word that you've touched down safely, there's a lot of cheering that goes on.
Oh, that's wonderful. 7 minutes of terror. I can only imagine.
I had some questions about the back heat shield.
Yeah.
I do have a picture on slide 11 showing you the heat shield. So this is the picture of the heat shield with the TPS ablator installed. We use a material called phenolic impregnated carbon ablator. It's actually a carbon weave that gets impregnated with phenolic. Phenolic is what ablates off that surface and allows the surface to stay cool enough that it doesn't soak back into the rest of the spacecraft. The next slide, you can see the overall aeroshell. Slide 12, please. So here's some additional hardware that's on board this aeroshell, in addition to, and most of it is mechanisms. I talked about the balance mass devices that are ejected. That was all part of the aeroshell mechanism. There's also 9 separation fittings that are fired in sequences of 3. That is all hardware that was built at Lockheed Martin and had to be tested. There's a Medley 2, which stands for Mars EDL Instrumentation 2. MSL also had that hardware, and it measures things like temperature of the surface, the amount of ablation that's occurring, the pressure on that front surface of the heat shield. All of that hardware is installed and will be active during the EDL event, so we get information for future missions. The back shell also has a ablator product on it. It's called SLA 561V. It's the same material that was flown back on the Viking program. So a lot of this, this technology has been used in the past. The structure itself is almost totally M55J composite materials. It has to be very, very stiff to withstand the high pressure of entry. There's 2.5 inch thick honeycomb on the heat shield structure that adds to that stiffness. So it's a seems very simple, but it's a very complex piece of hardware. So.
That it is, and it's got to withstand those extreme environments. So thank you so much for building that. So I'm seeing some questions about if there's aero braking and a little bit more on the entry, descent, and landing. And so, George, can you talk a little bit about the sky crane that Neil mentioned, and why is that the suited landing mechanism versus other landing systems?
If you're familiar with how the Curiosity rover landed, then to the untrained, well, it looks very similar, right? But there's actually a lot extra going on for Mars 2020 and Perseverance that you can't actually see. A lot of improvements. And part of that starts with the sky crane and the descent stage. And there's two key new capabilities that we're going to have for Mars 2020 that Curiosity didn't have. One is called range trigger, and the other is terrain relative navigation. Range trigger is all about when do you pop the parachute. Previous missions would be able to, as they're coming in to landing, they've got an estimated velocity and estimated distance of the surface, and they determined on when to pop the parachute based on their velocity, a certain velocity marker. We were able, by just changing one line of code in the system and using other measurements in terms of our range to the target, we're able to now to pop our parachute based on our actual estimated range to where we're going. What that helped us do was shrink the size of what we call the error ellipse or the landing ellipse. So where Curiosity was shooting for a target, ellipse that was 20 by 25 kilometers, we've been able to shrink ours down to about 8 kilometers diameter circle. So was really what enabled that, and then terrain relative navigation enabled us to choose Jezero Crater because it helps us get to more interesting landing sites that the scientists want to get to. Terrain relative navigation is very similar to how some of that is done here on Earth in different systems, but we have a downlook camera that's on the bottom of the rover, and as we're coming down with the descent stage, we're taking pictures, and the rover is comparing the images it's seeing to an onboard map that it's carried. This map was generated from the orbiters that we have around Mars, and the same ones that we use to pick the landing site. And on that map, we've marked out where are maybe some of the more dangerous places. And as the rover, as it's coming down, it can compare where it's headed with that hazard map. And if it looks like it's going towards one of those hazards, we have a built-in capability. It's called the divert maneuver. Curiosity did this too. After we pull away from the back shell and the parachute, we don't want that falling on top of us when we land. So we had a built-in divert maneuver. We used those engines to just go off in a direction. Curiosity, it wasn't a guided thing or a decision. It was just go in a particular direction. For us, we're able to use that same divert maneuver, and if it looks like we're headed to a more hazardous location, use that to go towards a safer location. So those are the two big new things that we have going on with our descent and landing. And definitely for those of our viewers, if you haven't seen it, I recommend searching for either 7 Minutes of Terror or Curiosity Landing. Watch the animated video animations of the landing, but it's coupled with the team as that is actually happening with Curiosity landed. It's very exciting because you're going from, once you hit the top of the atmosphere, you're going about 13,000 miles an hour. You're hypersonic. And then when you pull that chute, that's a supersonic parachute, that slows you down to about 1,000 miles per hour. Then you slow down using the descent stage, getting down to 200 miles an hour. And finally, we're only going about 1 meter a second, or 1 mile, a little over 1 mile an hour, when we gently set down that rover on the surface.
That's amazing. And I'd be remiss if I didn't mention the Aerojet Rocketdyne thrusters being used on the Sky Crane to lower it down.
And thank you. Thank you for providing those.
You're welcome. You know, I'm just going to highlight the propulsion throughout the mission. So now that we've safely landed on Mars, Katie, let's talk about the science. And you already talked a little bit about how you remotely operate, but what's your first thing you're going to do once we safely land on Mars?
Well, we're all going to heave a big sigh of relief and then let out a major cheer. But then, you know, we get down to business. And George mentioned the terrain relative navigation. And I just wanted to mention that, you know, that capability and the enhanced computer that allows Perseverance and Mars 2020 to do that terrain relative navigation is actually, we're taking advantage of that on the surface as well. And so we're using that faster, better computer processing to actually be able to traverse autonomously in a way that previous rovers have not been able to. So we think we can cover more ground every day with Perseverance than perhaps Curiosity ever was able to do, because we're basically with the rover surveying our landing site as we, you know, our terrain in front of us as we drive, and the computer is making decisions about where to drive. And so that's an exciting new capability that we have thanks to this better processing power that is also benefiting our entry, descent, and landing. But if we think about what we're doing on the surface, I mean, so we'll have hopefully our science mission plan in mind. So the minute we find out where we've landed, that'll all kick into high gear. So we'll think, okay, where did we land in this site? Do we, you know, what do we want to do here at this location? And where are we headed next? Of course, during the early days of the mission, we're doing a series of instrument checkouts and checking to make sure that our systems are operating nominally, and we come online piecemeal. So slowly we add capabilities every day. So the science team during this period of time is really focused on coming up with that science plan. And as we test out our instruments, we'll be selecting targets. And this is something that we do on other rovers. And we say, okay, well, we have this much time today. And we're using this instrument. Let's identify the most compelling scientific targets, and we put a plan together. And of course, there's lots of deliberation that happens while we do that. The scientists talk about what is most scientifically compelling, and then we talk to the engineers. And sometimes the engineers will say, sorry, can't do that. It's too dangerous, or we can't reach it. And then we have to go back in conference and say, okay, well, maybe we'll change our plan, or nope, we really want this rock. Can you get it for us? And so that kind of back and forth is one of the things that makes working on a rover mission, you know, so fun, I think, for so many people, is this working together as a team and doing that back and forth and give and take as you take hundreds of people to operate a single robot on another planet. And so it's a really unique experience that we have, and one that is very satisfying every day when you can come to a consensus about what to do on the surface, and then actually you get that data back. And so we'll be focused on that, you know, getting through those early days of Mars time when we're living on the Martian clock instead of the Earth clock. And those are, you know, those are fun, but kind of stressful days when you're walking around like a zombie sometimes because you're sleepy. But we do our best to make good decisions for the rover during that time, and that time is really essential to take full advantage of all the time that the rover has awake on the surface of Mars before we take our own human considerations back into account. So eventually we will transition off of Mars time. But then during that time, you know, that's when we are getting excited for our first sampling opportunity. We have ambitious sampling goals with this mission, and so we know that we have to get going, putting together that sample cache, because we hope that we have a rendezvous a couple years down the line with the next leg of Mars sample return. So we've got to get going, and we've got to do the science and collect the samples that will enable the next leg of that campaign. So we'll be thinking about that as soon as we get on the surface, and doing our best to plot a course and collect a suite of samples that will really feed, I think, generations of scientists when those samples come back. So we feel the responsibility, but we're excited to have that responsibility, knowing the potential for what it sets up in the future.
Oh, that's wonderful. So I know we're at the top of the hour. The panelists have agreed that they can stay longer, but and so we're going to talk a little bit about future Mars exploration, and then we'll get to more Q&A from the audience. But I just want to let folks know who did have somewhere to go that the panelists are going to stay. So let's move in. You mentioned the sampling. So Perseverance is collecting samples. So Neil, Lockheed's been a part of some previous sample return missions. And so can you talk a little bit about sample return missions and how you possibly could return samples from the Mars Perseverance rover?
Sure. So there's already RFIs in place for this next mission that you're talking about. It's going to be called Mars Sample Return. We recently completed a proposal for one of these RFIs to go off and build another aeroshell. This one, Mars 2020 aeroshell, was 4.5 meters in diameter. The next aeroshell for Mars sample return is going to be even bigger, believe it or not. It could be as big as 5 meters in diameter. So we were asked to propose this newer, bigger aeroshell. In addition, there's a new lander that's an even larger lander that's JPL will be responsible for. It's called the Sample Retriever Lander. And so this big lander has to get down to the surface, and its primary purpose is to go pick up the samples that Perseverance has left down on the surface. So the next mission to Mars will be close to where Perseverance is right now so that they can go pick up those samples. And then there will be additional missions that actually land a rocket down on the surface of Mars that could be used to take those tubes, stainless steel tubes that have samples from Perseverance, and fly those back to the US, or back to the world, the Earth, so that we can see what's actually down there on Mars and see if there's any signs of life. But those are missions out in the future. This particular RFI we just proposed to would launch in 2026. So we're talking about 4 or 5 years out. And then at the sample return mission is probably a year or two after that. So
great.
We're hoping to be part of all those. We love Mars, and we love going there whenever we have an opportunity.
Well, you have that in common with Aerojet Rocketdyne. We love Mars too. So gonna turn to George and just see, George, do you have any other additional thoughts on sample return missions? And then if not, what kind of planning is going on for future Mars robotic science missions?
Since Neil brought up the fact that there will be future missions that will need to go return these samples. We, Mars 2020, cannot lift off and come back home. And one thing that's very unique, I talked about the prior missions, and we kept building on prior missions and the knowledge. Each mission we've done has, taken the knowledge from prior ones and built on that. But this will be one of the first time where we've actually had hardware interfacing between 2 different missions launching in 2 very different opportunities. And so I want to illustrate kind of what that interface will be. So since I'm at home, I didn't have my usual props of my 3D printed sample tubes, but I realized that a little flashlight is about the same size as a sample tube. I even took my calipers to it, and it just so happens that this is roughly the same size and shape, even this little bulbous end of a sample tube. So we're carrying about 42 of these with us, and we'll be able to leave them on the surface. And so the future missions that we're talking about designing, we've already been working for the past several years creating what we call interface control documents. So basically agreements between our mission and future missions to be on, are there any requirements we have to actually place on these tubes, and how we can keep the samples, keep sample integrity for when we eventually get them home. And what do those future missions, how do they need to be designed to actually pick these things up and put them in some sort of container to come home. And continuing our flashlight analogy, the actual sample itself, it turns out it's pretty close to the size of a AA battery, maybe one and a half AA batteries. And so that's what we're talking about. This is going to be the goal that we get home. And if you can go to chart number 21, I actually have a picture of the real sample tube. This is part of our caching system. This is during thermal vacuum testing of it. And what we're doing in this image, is happening, we're testing putting the tubes in and out of their storage silos that we have to carry. We're able to, once the sample is in the tube, we have to bring it inside the rover, seal it up with a hermetic seal, a cap, and then we have two choices. We can either hang on to it for a bit and wait until we want to drop it, or we could drop it right there. Most likely our plan is we're going to be putting them back in the silos where we pulled them out. And then once we get to a location on the surface where we want to place this set of samples to await the future missions, then we would start depositing them there. We call that the depot cache approach. So all these future missions that we're starting to look at is we're in the planning stages now. And a big component of that is doing it with our partners in the European Space Agency. So some of the elements that Neil talked about, the retrieval landing system, landing a rocket, we call it the Mars Ascent Vehicle, that would lift off this set of samples, would be provided by, we're looking for being provided by NASA. European Space Agency is interested in providing what we call the Fetch Rover, such that if Perseverance itself isn't able to deliver the samples to that lander, a Fetch Rover, a smaller thing that's specially designed to go and pick up these types of tubes and bring it back to the Mars Ascent Vehicle. And then once it gets off the surface, there needs to be a return orbiter. And that's the third component of this sort of three major components: the sampling mission, that's us; a retrieval mission on the surface to get it off into Martian orbit; and then another mission that will rendezvous with that sample container that's in orbit around Mars and bring it home to Earth.
Wow, that's amazing. Thank you so much for sharing that and bringing your flashlight to explain it to us.
Oh, I got a new prop now. It's great.
Great. All right. So, Katie, as I mentioned earlier, I've got this great exploration rocket NASA does. It's the Space Launch System that wants to bring humans to Mars. So from your perspective, the science perspective, what needs to happen before humans go to Mars?
Well, I think going to Mars is kind of like planning a trip here on Earth. You don't go without having done a little bit of research about what the location is like and what the conditions are like, and perhaps what you need to bring with you and what you can get when you're there. And so in some ways, it's very similar to planning trips here, but in particular, we want to understand what kind of conditions our astronauts or Marstronauts would experience if they went to the surface of Mars. And we've been making progress on that question with previous missions as well. And in particular, one of the concerns that we have for astronauts when they're out in that space environment is radiation. And there's an instrument on the Curiosity rover called RAD, which has been measuring radiation since it was on its journey to Mars. And so we know a lot about from previous rovers. But with Perseverance, we have a weather station basically to understand pressure, temperature, humidity, dust in the atmosphere. And those are all very important pieces of information we would want to know if we were to send astronauts to Mars, to know what kind of environment they would be encountering and what kind of equipment they would need, how their spacesuits need to be built. And so our robotic explorers are doing some of that reconnaissance and data collection that can help enable planning for human exploration. Another thing we often think about is the in situ resources that Mars might have that astronauts could take advantage of when they're on the surface and perhaps don't have to bring with them, because mass equals dollars in a sense when it comes to missions like this. And so if there are ways we can take advantage of the resources that Mars has, we don't have to bring those things with us. So we think about things like understanding the climate cycle and understanding, water and where it is at the surface or a subsurface and ice and what conditions, what the weather's like to affect things like where those resources might be. And so those are the kinds of things that we think about and we want to understand, and what the material properties are of even the soils and the rocks are on Mars, because those could all be different resources that get used by astronauts in situ on Mars. So I think those are some of the things that we think about and that Perseverance in particular can contribute towards. And so each time we send a robotic explorer, we're making progress towards that goal of sending humans to Mars. And we can do that, fortunately, in a way that addresses interesting science questions for Mars about Mars's atmosphere today and the conditions on Mars, while also, in service to that goal of human exploration and advancing that part of our objective.
I love the sustainable approach that you all are really taking to exploration and taking it one step at a time. I think it's great, and I commend you for that. So before we get into the lightning round of questions, because we've got a lot coming at us, I wanted to ask Neil one thing about, he mentioned the Dragonfly that he's working on, which is going to send like a drone-like vehicle to Saturn's Titan moon. And so I wanted to know if you could talk about the lessons learned from the Mars 2020 Perseverance Rover and the Mars 2020 program, and how you're applying that to the Dragonfly mission, Neil.
Sure. So we're always gathering lessons learned from the various programs that we work on. Started back, at least for these big Mars missions like MSL, Mars Science Laboratory, we had to build a very similar structure, identical structure, essentially. It was considered to be build to print. So back on the MSL program, we actually built 2 heat shields instead of just one. We needed a second heat shield to do environments on, and that heat shield became a spare, which when we got on contract for Mars 2020, that piece of hardware was provided as government furnished equipment for us to save money on the Mars 2020 program and use that heat shield in addition to the new back shell that we had to build. Well, as it turns out, the biggest risk on the program for the aeroshell was that heat shield that was now 10 years old survived the static test. It had to go through testing just like any other piece of flight hardware to prove that it was capable of going to Mars again. And as it turns out, that heat shield was not adequately built to survive the new environment that was being imposed on it by Mars 2020. And we had a failure at that point. So we had to go back and figure out, well, what happened to that first heat shield? It was the first heat shield of its kind of that size. So we learned a lot. We figured out what went wrong with that first heat shield, and we fixed it for Mars 2020. So it's all information that will be used on this new mission called Dragonfly. Turns out Dragonfly wants a 4.5 meter aeroshell as well. So it's very applicable to use everything we learned on Mars 2020 and MSL on this new heat shield. We learned a lot about how to improve our processes, how to test the hardware early so you know that there's no issues with the hardware. We developed some new test approaches using IR thermography to look for disbonds of the structure. We did some testing by applying a film to the surface of the heat shield during the static test so we could monitor strain levels as you're applying more and more load to that structure. So that we've got tons of lessons learned. We've got a big long list. I've got the same people working on Dragonfly that worked on Mars 2020. So
that's wonderful.
Yeah.
All right, so we're going to go into lightning round where we're going to try to ask as many questions as we can and answer them as quickly as we can. So Christopher asked, what's the launch system? So I'm going to go ahead and answer that one for you. It's ULA's Atlas V rocket. Ashley wants to know, you said it uses nuclear power. Is that the type that converts nuclear directly to electricity? George, do you want to take that one?
Yeah, we use what's called a radioisotope thermoelectric generator, and we use the exact same type that MSL used. And the basic technology has been used for US space missions for decades, for 50 years. And in fact, Dragonfly, we use a similar system. And what it does is you have a small pellets of radioactive material, plutonium dioxide. It's a ceramic material that just heat. And we have several of those stacked up, and we have thermocouples wrapped around it. So it's a passive system. There's no moving parts. And those thermocouples directly convert that natural heat from radioactive decay into electricity. And for Perseverance, we get actually a twofer with the system. We don't, in addition to the electrical power, we also get the heat, which is what we need on the surface of Mars. So there is actually a fluid loop pumping through the rover to help transfer some of the waste heat from the RTG into the interior, what we call the warm electronics box, to keep the insides of Perseverance nice and warm. And that's what enables us to do what we need to do on the surface of Mars.
Awesome. And I'll also mention Aerojet Rocketdyne builds the nuclear power source for
That's right, you do.
The rover. So another Ashley wants to know, how long does it take to build a rocket? I think that's going to probably be best answered by the rocket provider, ULA, United Launch Alliance. So since we don't have them on this panel, I recommend if you go to their Twitter account and tweet them, I think it's at ULA Launch, they probably will answer that question for you. So next question from Joel. What opportunities might there be for citizen scientists to participate in the mission? Katie, is that something you want to tackle for us?
Yeah, you know, we've thought about different opportunities, and there are some opportunities already to do Mars research and assist with Mars research. And so citizen science, I think, is a growing area. We don't have anything at the moment that we have planned, but we're thinking about it in terms of thinking about identifying interesting places in the landing ellipse and perhaps, you know, opening that up and allowing, you know, our own community to take a look at the landing site and dig into the images and perhaps help us identify interesting locations. So we don't have anything that I can say that we've confirmed that we're going to do, but we're thinking about it, and we'll be sure to let you all know if we are able to kick something off like that. That's a great idea.
That's awesome. All right, so next question, George, this might be one for you, for Mario. Why are the wheels covered?
Oh, from the picture. Actually, if you can put one of those pictures of the rover with the wheel coverings. One of the, we're searching for potential evidence of ancient Martian life, right? Well, the first thing you don't want to do is bring some sort of Earth life with you and have our science instruments basically detecting Earth life. So one of the key things all Mars missions have done, this is part of what we call planetary protection, is, and that's why when you see these spacecraft being put together, they're in clean rooms to keep any potential of Earth contaminants as few as possible off the rover. So since the wheels themselves are what's going to be touching the surface of Mars, we want to keep them as clean as possible right up to the last minute. Katie, is there anything else you want to add to that, or did I hit it?
No, I think you hit it. I mean, we take it very seriously, the cleanliness of the rover and the system, because we want to make sure that the samples we get back, and the things that we find in those samples are indigenous to Mars and not things we've brought with us. And so we take that very seriously for this mission, particularly because of the sample return component. And so we've taken extra measures to keep the spacecraft clean and to protect our, what we call the sample intimate hardware, the parts of the rover that are going to interact directly with the samples. And so the wheel coverings are one example of ways that we try to keep the rover and the spacecraft clean as we're putting it all together and getting it ready for launch.
So the tires are a big question. So Patrick wants to know, how are the tires different on Perseverance opposed to Curiosity?
I can take that. So as some of you may have noticed, Curiosity is starting to get some holes in its tires. And this was not completely expected. And we, of course, we're doing a lot of things very heritage, trying to do as much build to print as we can. But even though the wheels are still, even though the part of the wheels have some holes in them, they're still perfectly capable and functioning. Curiosity can keep doing its mission for a long time. But we certainly thought that we'd like to maybe make some improvements. So what we did the test with various different types of sizes, size modifications to the wheels, also changes to the treads, because it actually, the tread shape on Curiosity is sort of a jagged chevron pattern. Turns out that actually is part of what was contributing to some of the holes. As we would roll across a particular rock, it would create greater forces there than it was designed. Oh yeah, thank you for putting that up. You can see on the Curiosity wheel that jagged, what we call the grouser. So for Perseverance, what we've done is we made the skin, oh, perfect. You'll see the skin of the wheel, it's still all the same material, it's all hogged out of a single chunk of aluminum, but it's slightly thicker, so it's more robust. But once you do that, you're adding weight, right? So how can you potentially offset that? So we've made the wheels slightly narrower. We also made them slightly larger in diameter. And then we changed the tread pattern there. We now have sort of a curvy wave sign. And it turns out that these wheels are actually much more robust. We have a test set up at the Mars yard at Jet Propulsion Lab, where we've run these wheels around and around and around, tens and tens and tens of kilometers, and they are just scuffed. So they're going to be quite durable for us. And on top of that, the new grousers actually give us a little bit better traction, so that we have a little bit more margin and a little bit more robust capability for going up or down slopes and sandy terrain.
Oh, that's awesome. All right, so we're gonna move on to our next question. How, if at all, is COVID-19 threatening the July launch? And this is coming from Julie. And then what preparation activities, if any, have been moved to a virtual environment?
I addressed that a little bit earlier, but I'll repeat. Certainly the COVID-19 situation, like many people around the world, had to adjust to the way we do work, particularly for our folks who are doing the mission critical work. The majority of our team has successfully transitioned to remote teleworking. Timing helped in this regard. Most of our hardware was completed and already at the Cape, and had already been transported there. So with the small teams that we still do need to have working on the hands-on critical hardware, like I said, we've kept the first priority is the safety of the team, as well as the community they're in. So we've been able to work with occupational health officials at our NASA centers, and taking guidance from Centers for Disease Control, as well as the local centers there at Jet Propulsion Lab in Kennedy, and been able to put in place practices so that our team can operate safely. And so far, we've been very successful. We are still on target for launch, so still making the milestones.
Awesome. Sunny wants to know, Katie, will Perseverance provide data to students, community, or universities for research?
Yeah, so all of the rover data goes out almost as soon as it gets back, and we have agreements to make sure that the rover data that we collect is available and accessible by the public. And so, for instance, the images that the rover takes, those are again available almost immediately once they come down. In terms of some of the other data sets that we have, usually they take a little bit of processing and preparation, but then they get posted, particularly on the it's the PDS is what it's called. It's a data repository, and we have an agreement to post the data there to the PDS. It's usually about kind of a 3 to 6 month time frame from the time that we get it. It's packaged with the proper files and explanation and put on the PDS, this data repository. And so yes, we make that data available to the public, and we encourage and are excited for those outside of the rover team to dig into that data and present science results and interpretations from that data.
Awesome. All right, I know we have just a little bit of time left. So Saita wants to know, should NASA collaborate with other international space agencies for Mars exploration like it does with the International Space Station?
I'll take that one. We absolutely do. In the game of space, we all can accomplish more if we're working together. Perseverance itself certainly has international contributions. If you can go to which one? There's the chart, the rover showing the instruments. Yeah, you'll see there's a couple of flags here. We have several contributions. Spain is contributing quite a few things. One is the weather station that Katie spoke about. Spain is also contributing the high gain antenna. So this is one of the main ways we communicate with the rover. They also provided that for Curiosity. France is contributing a large component of the SuperCam instrument. It's led by Los Alamos National Labs here in the US, but about half of it, some of the components are provided by France. We also have Norway. It's providing a brand new instrument we've never had on Mars. It's a ground penetrating radar. So this is another total new dimension. We're actually going to be able to, we've had orbital radars looking beneath the surface a bit, but this is the first time we'll be able to do it from on the surface. And lastly, Italy is contributing. It's not an active science instrument on our mission, but for future, they put a laser retroreflector. We put these on several, I think the InSight mission also had one, such that if in the future there could be a mission that has a laser ranging instrument, that we will be able to do some even better science in that laser ranging with these retroreflectors. And I also mentioned earlier about how for going forward with our future sample return activities, we are definitely working very closely with the European Space Agency to try to make that a joint and collaborative campaign.
Wow. All right. We got 2 minutes left. So Neil, 30 seconds or less. Tasha wants to know, is there a reason why the heat shield has a certain block configuration?
Yes, what you're actually seeing there is individual tiles. Just due to its size, you cannot machine a piece of TPS big enough to fit on the entire heat shield. So it's broken up into individual tiles. So you probably saw some of the lines in that image. Probably going to bring it up. So each one has its own reason for being the shape it is. You can see some highly triangular shaped tiles there that are there due to the heating at that particular point on the heat shield. So that's the reason, and there's reasons. That's good enough.
All right, so our last 1 minute together. Tell me what you're most excited about for this mission, or what inspired you to get into Mars exploration. So Neil, I'll start with you.
Okay, well, it goes all the way back to childhood. My father was very enthused about space, and I initially got into SD's rockets when I was a very young child. We built a Mars lander, believe it or not. If you look at some of the concepts for Mars landers for people to go to Mars, it's very similar to that, that was probably, that we built probably 50 years ago, believe it or not. So that got me kind of enthused about space. The Viking landers that landed in 1976 I was very excited about Martin Marietta. It was where my parents lived. I really wanted to go to work for Martin Marietta at the time. And I finally got a job in 1984 working for them. Now it's Lockheed Martin, but that's what got me excited.
Awesome. I'm glad you were able to get on with them in 1984. All right. So Katie, what are you most looking forward to, or why did you get into Mars exploration?
I'm most excited to look for biosignatures in that delta. That's the big thing that I'm looking forward to. In terms of how I got interested, you know, I thought I wanted to do astronomy, and I was really interested in stars and you know, things that were very far away. And I had the great fortune of taking a geology class in college, and I realized, wow, you know, here I am with my eyes focused outward, and I don't know anything about the planet that I'm actually on right now. And I think that had a big effect in helping me focus on planetary geology and trying to take what we know and understand about our planet here on Earth and use that to inform what we know about other planets. And that led me directly to Mars, which in some ways is very Earth-like, in other ways not at all Earth-like. And so for me, Mars is a great place to work, and a way to translate the kind of, or to combine something that we know and understand very well with something that we've never done before, and exploration of a place we've never been before. So to me, that's this perfect combination of the known and the unknown. And it's why I'm so excited to explore Mars, and I'm very excited for what we'll find with Perseverance.
How cool is that you get to say I work on Mars? That is,
I know, it's pretty amazing.
That's awesome. All right, George, take us home.
Yeah, I kind of echo what Katie said. I'm most excited about this. There's so much going on, as I said, lots of neat technology. Science instruments are awesome. We're going to get great science. But I'm just generally excited about the concept of exploring a new place on the surface of Mars, a different type of terrain than we've seen, at least what we can tell from orbit. I remember I was fortunate enough to be in the at JPL and in some of the with the science team when we got some of the first images from Spirit and Opportunity, and seeing how diverse those two landing sites were, and then with Curiosity. Landing in that environment, and then being able to look at that terrain and see the crater wall off in the distance, and then Mount Sharp just right there begging to be climbed. So I'm super excited about seeing that, some of those first pictures when we sat down in Jezero crater and that delta, you know, being able to go about that new terrain, heading across it, and then maybe even up and over the crater rim. I think that's what I'm most excited about, getting the samples, bringing them home, and really beginning humanity's first round trip to Mars with these samples.
Thank you. I want to thank all of our panelists and thank Explore Mars for putting on this wonderful event. Hopefully everybody has enjoyed it. I think it was an outstanding event. I know I learned a lot today. So thank you very much. And if you haven't checked out the Perseverance Twitter account, I recommend. It's tweeting about what it's up to in the first person. So it's a lot of fun. And then JPL has a Twitter account, NASA has a Twitter account, Aerojet Rocketdyne has a Twitter account, Lockheed Martin as well. All of us have social media accounts, so you can follow along and prepare for the launch in July, and then hopefully the landing on February in 2021. Thank you all, and I'll turn it back over to Chris Carberry.
Oops, let's see, 1 second. There I am. Thank you, Mary. Thank you, panelists. That was spectacular. I don't have much else to say, but thank you, everybody, for coming on. We will be announcing our next week's session very soon. In the upcoming weeks, we'll have sessions on the 30th anniversary of the Hubble Space Telescope, as well as a mission architecture, Humans to Mars mission architecture panel coming up, and quite a few other topics. So stay tuned. We have a lot of great webinars coming up. So once again, thank you to everybody who came on and to our panelists. Have a good day.